In this lecture, we will focus on representation of single sideband signals. If you recall, in the last lecture we discussed suppressed sideband modulation. So, in that there are two types. One is single sideband modulation and the other one is vestigial sideband modulation. Now, you can suppress any one of the sidebands. For example, you have the message signal m of t and this one is modulated by your carrier, let us say a suffix c cosine omega ct, and this is your double sideband suppressed carrier. That means in this point you have double sideband. I need to remove any one sideband, right? Either you remove the upper sideband or you remove the lower sideband. You put a sideband filter. So, the sideband filter removes any one of the filter based on the type of filter that you employ there. So, this is your single sideband filter. Now, up to this point I know the expression. What is, let me call this is x of t. What is x of t? X of t is equal to m of t times ac cos omega ct, no problem. Now, the next question is, can we write the time domain expression in the output? So, how do you write? So, that is a thing that we are going to discuss in this lecture. Okay. So, I want to write an expression for the SSB waveform in time domain. To do that, I will start with the frequency domain, because single sideband signal is very easy to understand in the frequency domain than in the time domain, okay, but not so easy to understand, that is not so easy to understand in the time domain. So, let me start from where it is easy to understand. Let us say we generate a SSB signal from the DSB signal. So, this point I am getting the DSB signal and low pass filtering. Low pass filtering means what? You are going to retain the lower sideband. Let us say this is my m of f, capital M of f, spectrum of your message signal. Your DSB SA will be like this, and then like that. Now, this is FC B0 minus B, FC plus B, FC minus B, and there is a frequency axis 0 minus FC plus B minus FC, and this point is minus FC minus B, and this one is lower sideband and this one is upper sideband. This is lower sideband and this one is upper sideband. Now, I would like to retain the lower sideband. So, what you do? You multiply by a low pass filter like this. Okay, I have drawn in the green color signal like this, or I can draw it separately, no problem. Okay, extend this, extend like this. You put a low pass filter, and this is HLP of f. LP means low pass. If you multiply, this one is let us say x of f, multiply x of f and low pass filter, then the output will be like this, like this. Only lower sideband is retained, upper sideband is rejected. Okay. Therefore, if you multiply, if you put a low pass filter here, low pass filter, then lower sideband is retained and upper sideband is rejected. Okay. So, therefore, I must multiply the message spectrum, I mean modulated signal spectrum, DSB modulated spectrum by the low pass filter. Okay. Now, let us try to find the transfer function of the ideal low pass filter, which looks like this. So, this is my ideal low pass filter. Okay. Now, the product of this ideal low pass filter and x of f gives lower sideband signal. So, this is a process through which Ssb waveform is generated in the frequency domain. Okay. So, now let us look at this ideal low pass filter, and I can represent this ideal low pass filter as the sum of two signum functions. Before that, we need to recall certain basic things so that we can represent the low pass filter in the frequency domain. For signum function, we know how does it look like. In the positive side it is plus 1, in the negative side it is minus 1. Let us say this is f and this one is signum of f. Okay. So, now what is minus signum of f inversion of this? This will be it will be like that. This is minus signum of f. Now, let me delay this minus signum of f by fc. So, let us say this point is fc, then therefore, my signal, maybe I will use some other color. Like this. This is minus signum of f minus fc. In case if you scale the amplitude by 0.5, then the same signal will looks like this. Like that. This is minus 1/2 signum of f, right? That is it. So, this is one part that we need, and the other one is recall from this guy. So, what I am going to do, I am advance this signal, the signal by an amount let us say minus fc. So, therefore, the signal looks like this. What is this? This is signum of f plus fc. Now, again scale the signal by half, then this will be sorry. So, this is half signum of f plus fc. Okay. Take this signal, half of signum of f plus fc and minus half of signum of f minus fc. Add these two guys. Okay. So, let me add here. This one is like this. This is half of signum of f. So, let me extend this point like this and this point also like that. Now, before that it is like this. It is coming from minus infinity to plus infinity, frequency axis is. This point is minus fc, and this point also minus fc, and this point is plus fc, this is plus fc, right. Now, add these two guys. If you add, in this portion the value is minus 1/2. Okay. So, from minus infinity up to minus fc, its value is minus half. Now, what about here? This one is up to here, it is plus half. Okay. Minus infinity to minus fc, its value is plus 1/2. If you add these two, what will you get? You will get a 0 component. Okay. So, you will get up to this point you will get 0. Fine. Now, let me change the color. Now, you take minus fc to plus fc. and here also minus Fc2 plus Fc. In this region the value is 1 by 2, here also 1 by 2, 1 by 2 plus 1 by 2, it is 1. Therefore, you will get like this one, sorry, you will get 1 like that. Okay. Then now from Fc to infinity it is minus 1 by 2, and in this one from Fc to infinity it is plus 1 by 2. If you add these two guys, then you will get a 0. Therefore, what is this? This is the low pass filter of cutoff frequency Fc and minus Fc. Therefore, my low pass filter can be written in terms of two signum functions. One is delayed by Fc and another one is advanced by Fc. Okay. Sorry, this is I wrote wrongly. This is not F. This is F minus Fc, and this one is F plus Fc. Okay. So your HLP is summation of these two guys, 1 by 2 signum of F plus Fc plus minus 1 by 2 signum of F minus Fc. Therefore, I can write HLP of F is equal to 1 by 2 signum of F plus Fc advanced one minus 1 by 2 signum of delayed version F minus Fc. So, this is the mathematical expression for my low pass filter in terms of signum function. Now, you multiply your modulated signal DSB modulated signal with a low pass filter. Therefore, you look at the figure which we started with. This one is x of t. Let me change the color. This one is x of t and here x b of t. If you take Fourier transform, this is x of f and this filter has h low pass filter of f. So, this is let us say x Ssb of f. So, x Ssb of f is equal to x of f times h suffix low lp of f. That is all. You multiply the Fourier transform of x of t and the filter transfer function h low pass filter of f. That is it. Once you get this x Ssb of f, then you take inverse Fourier transform, you will get the time domain expression for single sideband modulated signal. That is the overall theme of this lecture. Fine. Now, take the same figure, your modulated signal, it will be like this. This is x of f and like this plus Fc minus Fc. Then now this whole portion, what is this? This is m of, maybe I will one more time, just to hold on a minute, because if you do not understand this, it will create a lot of confusion. So, let me plot first m of f. Let us say my m of f is like this. Okay. After modulation, your DSB modulation, it is going to be like this. That means what? The whole m of f, is delayed by an amount. How much amount? Fc. So, what is this whole guy? This is m of f minus Fc. Do you understand? Similarly, the left hand side also you have something like this. The m of t is advanced by an amount of minus Fc. Therefore, this whole thing is m of f plus Fc. Okay, so both the lower sideband LSB and upper sideband both are denoted by m of f plus fc, and here in the positive frequency axis both the lower sideband and upper sideband both are denoted by m of f minus fc. That means your message signal is delayed, and here your message signal m of t is advanced operation. That's all. These two operations you are doing now. Then what you are doing, you are multiplying these guys by two signum functions, because your low pass filter essentially consists of summation of two signum functions. Okay, one is starting like this, like that. And what is this signum function? The signum function is 1 by 2 signum of f plus fc. Now if you multiply these two guys, what will you get? This is x of f. If you multiply x of f and 1 by 2 signum of f plus fc, okay, here this portion will be rejected, and but let me denote this. Let me choose some other color. This area will be multiplied by this area is denoted by what? M of f plus fc, these two guys. Okay, now if you extend this, it is multiplied these two things. Okay, here its value is 1 by 2. Here its value is 1 by 2. So the whole, this shape is not changed. Shape is not changed, and the location also not changed, but only it is multiplied by 1/2. Therefore, m of f minus fc times 1 by 2 signum of f plus fc is equal to same. Therefore, that is the first rule that we will derive here. M of f minus fc times 1 by 2 signum of f plus fc. This is equal to 1 by 2 m of f minus fc. Why? In this range, your signum of t is how much? Your signum of t is a constant value of 1 by 2. Okay. Therefore, this 1 by 2 is coming, and the signum of f, no need to put it here. Please remember, understand that. In fact, if you want to know still very clear explanation, you don't write this one. Okay. Let me write down x of f. So now m of f minus fc, but what is your x of f in this range? It is 1 by 2. So you multiply by 1 by 2. So therefore, this is 1 by 2 m of f minus fc. Okay. So what is x of f? X of f is denoted by this signum function. Let's say 1 by 2 signum of f minus fc. Okay, that's it. So this is one result. Similarly, you can derive one more result. Before that, let me multiply these two guys. Okay, therefore the output is, recall from the figure, your x suffix ssb of f is equal to x of f times h low pass filter of f. Let us multiply, and then we will come back to this thing. Okay, so x suffix ssb of f is equal to x of f times low pass filter HLP of f. What is x of f? X of f is AC by 2 m of f minus fc plus AC by 2 m of f plus fc. Okay, or you put a delayed component first and then advanced advanced component first and delayed component next. Okay, the whole thing is multiplied by your low pass filter. What is your low pass filter? Half times signum of f plus fc advanced component minus delayed component 1 by 2 signum of f minus fc. That's it. You multiply these two things. Okay, so let me say this is term 1, second term, and third term, and fourth term. So there are 4 terms. You multiply these two, then you'll get 4 terms. Okay, and this is the expression for DSB. No, this is the expression for DSB SC, and this is the expression for low pass filter. Okay, so what are we doing here? We are multiplying this spectrum, DSB SC spectrum, with the transfer function to produce an SSB output. Therefore, my expression for the SSB spectrum in the frequency domain can now be written in the closed form. So that's what we are doing now. Okay, so it will have many terms. You are multiplying 2 terms, okay, in one expression and 2 terms in the other expression. So totally we have 4 expressions. So term by term we will multiply now. So AC times AC by 4 m of f plus fc, then signum of f plus fc. This is my first term. Then minus AC by 4 m of f plus fc, signum of f minus fc. This one belongs to first and fourth term. Then second term with the third term, AC by 4 m of f minus fc, then signum of f plus fc, then minus AC by 4 m of f minus fc, then signum of f minus fc. Okay, now that's it. So these are the 4 terms, okay, that you will get. Now if you look at it carefully, I can collect these 4 terms into 2 groups, right? So let us take this term AC by 4 m of f plus fc. Let me name these terms. Let's say this is A term, this is B term, and C term, and D term. There are 4 terms now. So you take the B term. What is the B term? B term says m of f plus fc, signum of f minus fc. Okay, so take this minus sign also here, minus. So that means m of f plus fc minus signum of f minus fc, like this. What is this? If you look at the figure, then in the modulated spectrum, this is my m of f plus fc, and this one is you are multiplying, sorry, like this. I'm sorry, wait, hold on. Maybe let me draw here like this. What is this? M of f plus fc, then signum of f minus fc will be like this. Now you multiply, this is my signum of f minus fc minus 1 by 2. Okay. Now let us, for the time being, let us forget about this minus 1 by 2. Then multiply signum of f minus fc times m of f plus fc. So in this portion, this is constant. Okay. Therefore, if you multiply these two guys, m of f plus fc times signum of f minus fc, then this is equal to m of f plus same fc. If you multiply, you will get the same thing like that. No change. Therefore, no change. Look at, convince yourself. After multiplication, again you will get a same m of f plus fc. Okay. So this area is multiplied by this area. Based on this constant term, this height is reduced. That's all. Okay. So therefore the b term becomes m of f plus fc times signum of f minus fc. Your b term is going to be minus, it is ac by 4 m of f plus fc. Now look at the c term, m of f minus fc times signum of f plus fc. So in the same expression, what you do, you put like this. This whole thing is what? M of f minus fc. Multiply that m of f minus fc with the a function minus signum of f plus fc. Okay. So signum of f plus fc will be like this. So this area you are multiplying with this area. So in this area it is constant. And by the way, what is this function? This function is 1 by 2 signum of f plus fc, and this one is f minus m of f minus fc, and this is 1 by 2 signum of f plus fc. If you multiply these two guys, m of f minus fc times 1 by 2 signum of f plus fc. So this is equal to, because this is constant in this region, you forget about 1 by 2 for the time being. Okay. So this is m of f minus fc. So m of f minus fc multiplied with the signum of f plus fc is m of f minus fc. For the time being, let us not worry about this 1 by 2. So the same thing we are doing here. So m of f minus fc multiplied by signum of f plus fc. Therefore the c term becomes ac by 4 m of f minus fc. Right. So and this minus sign will go away. Why? Because you are multiplying m of f minus fc with the minus, this is minus signum of f. Where is it? Yeah, this function, one second. Okay, this function is, let me change the color, minus 1 by 2 signum of f minus fc. There is a minus sign. Okay, so here you put a minus sign here. So this b expression I can write as follows. B expression is AC by 4 m of f plus fc times minus signum of f minus fc, and these two guys becomes what? AC by 4 m of f plus fc. This minus will be observed. Because of this minus only you are getting this wave shape. Okay, you are getting this shape. Okay, therefore that minus will go away. So that is your b term. B is equal to AC by 4 m of f plus fc. Similarly, your C term becomes AC by 4 m of f minus fc signum of f plus fc. But in this case there is no minus term here. Okay, this is signum of f plus fc only. Okay, but this one is minus 1 by 2 signum of f minus fc. Because of this minus, that minus, and this minus is observed. Okay, fine. So this will be equal to AC by 4 m of f minus fc. So I have two terms from B and C. That's it. Okay. So now let us look at a D term and A term. Okay, let me take A term first. AC by 4 m of f plus fc plus signum of f plus fc. What is A term? A term is AC by 4 m of f plus fc signum of f plus fc. Now how do you find out this term? This is not very clear. Okay, so let us try to understand this part in the time domain. Okay, so this expression is not clear in the time domain how it will look like. So let us start with this guy, A term. Okay, this is where the Hilbert transform comes in very handy. Remember, the Hilbert transform is defined in terms of signum functions in frequency domain, and we are having signum functions here. Okay, so there is a relevance, so we use Hilbert transform. If you recall, Hilbert transform of m of t is minus j times signum of f times Fourier transform of your m of t. Okay, this m of f is the Fourier transform of m of t. Now the Hilbert transform of m of t is nothing but minus j times signum of f times Fourier transform of m of t. So this is a formula that we derived in one of the previous lecture, please recall. Therefore the Hilbert transform of m of t is nothing but you multiply minus j signum of f with the spectrum of m of t in the frequency domain. Okay. So also you recollect the basic frequency translation theorem. M of t, if you take Fourier transform, you will get a capital M of f. You multiply m of t by e to the j 2 pi fct and m of t. If you take Fourier transform, then it is going to be m of, shift in the frequency domain, m of f minus fc. Right? Suppose if we multiply e to the minus j 2 pi f c t times m of t, then Fourier transform will be, recall this is Fourier transform, okay, not Hilbert transform, m of f plus fc. If there is a minus, then it becomes plus. In general, we would like to write like this, plus or minus j times 2 pi fct times m of t. This becomes m of f minus or plus of fc. Okay. So, this is your basic properties from your Fourier transform. Okay. So, let me call this whole thing as the first one. And from Hilbert transform, what is your m cap of t? M cap of t, Hilbert transform of m cap of t is, just now I said, minus j times signum of f times m of f. And the third property that also we did in the class, Hilbert transform of m of t multiplied by e to the j times 2 pi f c t becomes minus j times m of this f must be replaced by f minus f c. Okay. Let me put a plus or minus here. Okay. So, if I put plus or minus, then it becomes minus or plus f c, then signum of f minus or plus f c. So, this f becomes like this, and this f becomes shifted minus or plus f c. Okay. Recall these three properties. So, we keeping these three basic results in mind. Now, let us look at the inverse Fourier transform of the last two terms, second one and the third one. Sorry, let us try to take the inverse Fourier transform of at least this guy, this term. Okay. What is a term? A term is AC by 4, then m of f plus fc, signum of f plus fc. Okay, now compare this and that. Okay, you put AC as it is, AC by 4, m of f plus fc, signum of f plus fc you have here. Okay, in the time domain, this j becomes in the denominator and a minus sign will come. So, minus 1 by j, this whole term, m cap of t. If we have plus, then e to the minus j 2 pi fct. Okay. So, convince yourself. Or else before that, because it will create lot of confusion, maybe write down one more very clearly. Now, in this one, m cap of t e to the minus j 2 pi fct. If you take Hilbert transform, I am taking Hilbert transform, okay, not Fourier transform, please remember. Sorry, Fourier transform only. Already I have took Hilbert transform, okay. So, this is Fourier transform only. Fourier transform, this is the Hilbert transform of m of t. So, you are taking the Fourier transform of Hilbert transform of m of t, which is multiplied by e to the minus j 2 pi fct. Therefore, this is minus j times m of, if there is minus here, this minus becomes f plus fc, signum of f plus fc. Now, multiply both sides by minus. So, minus m cap of t e to the minus j 2 pi fct. Fourier transform is equal to j times m of f plus fc, signum of f plus fc. Now you bring this j to the left hand side, okay, minus 1 by j Hilbert transform of m of t times e to the minus j 2 pi f c t. If you take Fourier transform, by the way, this is Fourier transform. Okay, this is going to be m of f plus fc signum of f plus fc. Now multiply both sides by a by 4. So ac by 4, already I have minus 4j m cap of t e to the minus j 2 pi fct. It forms a Fourier transform with ac by 4 m of f plus fc signum of f plus fc. That's it. Now this is precisely, don't you see, this is the a term from the given expression. Okay, where is the a term here? It is over there. Yeah, ac by 4 m of f plus fc signum of f plus fc. So this can be written as minus ac by 4 then divided by j m cap of t e to the minus j 2 pi fct. Okay. Similarly, if we put ac by 4 m of f minus fc signum of f minus fc, then this becomes minus ac by 4 m cap of t e to the plus j 2 pi fct. This also Fourier transform. Okay, and that one is precisely, where is the term? D term. So we are taking D term and A term, A and D, m of f plus fc times signum of f plus fc, and then m of f minus fc times signum of f minus fc. Okay, and there is a minus sign here. Fine. So you have minus ac by 4 m cap of t e to the j 2 pi fct, this guy, and this guy has one more minus sign. If you multiply minus here and this will become plus, so this will be plus. Why this minus sign comes? Because from the this expression, this minus, this minus. Okay, look at this, there is a minus sign here. Okay, this minus is coming over there. This one, that's it. So, and then this becomes minus ac by 4j, then m cap of t e to the minus j 2 pi fct. Rearrange these guys, ac by 2, m cap of t also constant, you can pull out. Then within the bracket e to the j 2 pi fct, sorry, minus e to the minus j 2 pi fct whole divided by 2j. And this is sin 2 pi fct. Therefore, AC by 2 m cap of t sin 2 pi f c t. Okay, so this is the inverse Fourier transform of these two terms. What are those two terms? A term and D term. Okay, these two terms, A term and D term. A and D terms. Similarly, inverse Fourier transform of B term and C term, just now we got it. Where is it? See, B and C is here. This is B and this is C. You combine these two guys, AC by 4 m of f minus fc plus AC by 4 m of f minus fc. You take inverse Fourier transform of this. AC by 4 m of f minus fc becomes m of t multiplied by e to the j 2 pi fct. Okay, one is plus and one is minus, plus AC by 4 m of t e to the plus j 2 pi fct. Now m of t is common, AC is common, you can pull out. Maybe I will write down here B and C, B plus C, AC by 4 capital M of f plus fc plus AC by 4 capital M of f minus fc. Okay, now AC by 4 is constant, you can pull out. M of f plus fc. Okay, frequency shifting theorem from your Fourier transform. If you take inverse Fourier transform, this becomes e to the minus j 2 pi fct m of t plus this guy becomes e to the plus j 2 pi fct and m of t. Now m of t is common, you can pull out. So m of t times AC by 2, then rearrange this e to the j 2 pi fct plus e to the minus j 2 pi fct whole divided by 2. So this is AC by 2 m of t cos of 2 pi fct. So this is due to the inverse Fourier transform of B term plus C term. Because our ultimate aim is we need to find out the time domain expression. Okay, so this is B plus C. You sum up all the four terms now. So this is A and D. Therefore, in the time domain, x suffix ssb of t is equal to A term inverse Fourier transform of A plus B plus C plus D term. Now A and D gives one component, B and C gives one component. Just now we looked at B and C gives AC by 2 m of t cos of 2 pi fct. Then C and D gives AC by 2 m cap of t sin of 2 pi fct. That's it. So very interesting. Okay, so this is x ssb of t. So it gives me the closed form mathematical expression for the single sideband signal in terms of the message signal m of t and the carrier cos omega ct. Okay, just like we had for the DSB signal, double sideband suppressed carrier signal. Yeah, very neat and interesting expression this one is. I hope you followed the derivation. It is fairly straightforward, but we should be very careful. It involves a lot of properties from your Fourier transform and Hilbert transform, nothing else. Basically it makes use of the properties of Fourier transform and the properties of Hilbert transform. If you know these two properties, then you can easily work on it. Now what kind of expression this is? It is a lower sideband signal. Okay, so we are retaining the lower sideband and rejecting the upper sideband. Now it is a very simple exercise for you to go through the whole process again and show that instead of the minus sign, if you put instead of the plus sign, if you put a minus sign, then you get the upper sideband signal. Okay, this one is for lower sideband. If you want XSSB of t for upper sideband, this is equal to same expression AC by 2 m of t cos of 2 pi fct plus AC by 2 m cap of t sin of 2 pi fct. Okay. Lower sideband. The whole process, you repeat once again, and you will end up with the, I am sorry, again I did a mistake. Why did I put like this? That's it, minus symbol. That's it. That is the only difference for upper sideband. Okay, so it is a very interesting and useful expression, and this is a mathematical closed form expression for the SSB waveform. It is not easy to visualize this waveform in the time domain. Why? Because to visualize this x suffix SSB of t, not only you have this term AC by 2 m of t into cos 2 pi fct, but also you have the Hilbert transform of m cap of t. Okay. So for arbitrary signal, one doesn't know how m cap of t will look like. Okay. So for example, if we have cos omega ct and take Hilbert transform, then it will be sin omega ct. We know how the waveform looks like this. Similarly, if we have sin omega ct and if we take Hilbert transform, it becomes minus cos omega ct. So we know the Hilbert transform of sin and cos, but we don't know how the waveform will be when you take the Hilbert transform of an arbitrary signal. Okay, so for certain kind of signals, one can work it out, like cos omega ct and sin omega ct. Okay, so like I can say the Hilbert transform of cos omega ct is sin omega ct. But for an arbitrary waveform, very difficult to see what the Hilbert transform will look like. So in general, it is very very difficult to visualize. But for a specific kind of waveforms, it may be very easy to visualize, like sin omega ct or cos omega ct. So this is a mathematical representation of single sideband signals in the time domain. This representation leads to a second method of generating SSB waveforms. This method is called a phasing method. Okay. So now let us represent in terms of figure. So maybe I need some space, so let me delete this. Okay, let me start now. Now m of t, and this m of t is given to a multiplier. You have a source. Let us say the source is producing AC by 2 cosine omega ct, and this one is, what is the signal? AC by 2 m of t cos omega ct. That's it. Now here what you do, you put a 90-degree phase shift, so that you will get a AC by 2 same sin omega ct. Now this m of t you give it to Hilbert transform, and this one you multiply with this guy, and after Hilbert transform, see in this point you have m of t, m of t, in this point you get m cap of t and this output is AC by 2 m cap of t sine of omega c t. Take these two guys and put an adder, that's it. This is your x Ssb of t, that's it. So it looks very neat and very simple diagram. Okay, so this is the second method. The first method requires, see we discussed two methods, right? The first method requires high Q tuned filters, okay, around the carrier frequency to remove one of the sidebands. But the second method looks very simple, but actually difficult, okay, still difficult, that difficult still remains. Okay, that means the difficult has been passed on from the realization of high Q band pass filter to an ideal Hilbert transform. Here we need a ideal Hilbert transform. Again, this also difficult. Okay, so we need to realize the ideal Hilbert transform. Remember, an ideal Hilbert transformer will have to affect the phase shift of minus 90 degree for each and every component in the bandwidth of the message signal, starting from 0 hertz to whatever is the bandwidth up to B hertz. For example, this is your message signal, start from 0 to B hertz. Such an ideal Hilbert transformer is also not easy to visualize. However, since the whole operation has to be done around the baseband, therefore the Hilbert transformer which operates on the baseband 0 to B baseband signal is much easier to approximate than to realize the high Q tuned filters which is required for the Ssb filter. And both methods are used in practice. Both are used in practice. Okay, the first method as well as the second method. And of course, both the methods have their own pros and cons. But the second method gives you an alternative. The second method is called phasing method. Because this requires the implementation of a 90 degree phase shift. Okay, we require a 90 degree phase shifter, not at a single frequency. Suppose you say 50 hertz signal, and if you want to introduce 90 degree phase shift, then it is easy, no problem. But what we are saying is, we want to introduce 90 degree phase shift not only for single frequency, we need 90 degree phase shift for a band of frequencies, right from 0 hertz, let us forget about 0 hertz, 1 hertz, 2 hertz and 3 hertz and so on up to B hertz. For all these frequencies, I need a constant 90 degree phase shift. So realizing a 90 degree phase shifter at a single frequency is a trivial job. Okay, so this is a trivial job. You simply put a R and C and it will give the 90 degree phase shift. You can think of a very simple circuit consisting of only R and C, and that can do that. But in fact, ideal capacitance would produce a 90 degree phase shift. But to realize that for a band of frequencies 1 hertz to B hertz, let us say B is equal to 4000 hertz. Okay, it's very difficult. It is not easy. It is difficult to get a constant 90 degree. This is not a simple thing. Okay, I need a constant 90 degree phase shift over this entire band. So that's why this also has some pros and cons, and high Q tuned filters also has some pros and cons. In practice, both of them are used. Okay, So that's all about single sideband waveform generation and its representation. Okay, so in one of the previous lectures we have already talked about demodulation of Ssb waveform to some extent. Okay, now in the next lecture I like to come back to the demodulator of Ssb signal, single sideband signal. Now one can ask a question, what kind of modulator do we use to demodulate the single sideband signal, and what do we call it? Namely the synchronous demodulator or coherent demodulator. Okay, and again when I say synchronous demodulator, then I need to have a local carrier, and that local carrier must be in phase with the incoming carrier, and there will be frequency synchronization with the frequency synchronization. Okay, so let us talk about this in the next lecture. Thank you.